Hello AAF kids, and we're here for another snow day, right? So we need to keep moving with our lessons, so I'm going to make two videos. One to go with today's lesson, and then another one to go over all the homework problems, because there's some easy ones and then there's some more challenging ones towards the end. You know, about half of them were kind of routine and half of them had some tricky parts to them. And as you can see from my warm-up slide, you have a quiz on Friday. So, and it's graphing. It's just going to be one graphing characteristic test. So notice that I have given you homework problems, 3 problems in the book, and characteristics. The handout, though, that I would have given you is the last slide of this presentation. So we're really going to do this part of the homework together. Alright, so let's go ahead and start the warm-up. Notice I just want domain and range. I'm going to do the domain for all 3 first. And factoring this denominator gives me 2 bad x's. This was linear, so I only have 1 bad x. This is linear, so I only had 1 bad x. There's the domain. Now, the range, in order to do the range, as I taught you before, you're going to write all real numbers and then your suspects. And your suspects are any, I might have to kick out a y value of a whole. I might have to kick out a y value of a horizontal asymptote. So first I have to figure out if I have a whole or vertical asymptote. And as you remember, we did that by looking at the factors of the denominator compared to the factors of the numerator. Since there were no matching factors, both of my bad x's were vertical asymptotes. So since both of them were vertical asymptotes, I don't have any holes. So no suspects there. Now I have to look at horizontal asymptotes, and I taught you on Friday that to look for a horizontal asymptote, you look at the degree of the numerator and the degree of the denominator. For rational functions, you don't have to go through the pain of actually exploring the end behavior by plugging in very, very large numbers for x and very, very small numbers for x to see what the behavior is. You can just look at the power of the numerator compared to the power of the denominator. And since you are bottom heavy, you are going to have a horizontal asymptote at y equals 0. But remember, this is still a suspect. I don't know if I need to kick 0 out of the range. And how I figure that out is I ask. You take the y value of 0 and you replace f of x with 0, because f of x means y. So I say, excuse me function, is there any x that will make you equal to 0? And from elementary school, I learned that if I want a fraction to be equal to 0, the numerator has to be equal to 0. So I say, hello numerator, what x will make you equal to 0? And I get -3. What does that mean? That means when x is -3, y is what? 0. So y goes with the x of -3, y of 0, which means you do have a horizontal asymptote that this function will not touch at the ends, but in the middle, as a matter of fact, at the x-intercept, this function will cross the ha. So that means that y equals 0 is cleared, right? You didn't have any holes, so there were no suspects there. You had a suspect of 0, but because I got a good x, right, this was not kicked out of my domain, then I know that this is a point that exists where y is used. So therefore, my range is all real numbers. Okay? Let's do the same thing here. What is my range? All real numbers. And my suspects, any y values of a whole, the y values of horizontal asymptotes. This time I factored the numerator, and I got x minus 2 and x minus 1. But x minus 2 factored out and left me with just x minus 1 over 1. So I had one bad x. That bad x was did go with the factor that canceled out, so my vertical asymptote was shrunk to a whole. So I do have a whole at 2 what? 2 is the x value of the whole, but what's the y? Remember, you take the 2 up there, and 2 minus 1 is 1. So that's a y value of the whole. Now I look for a ha, and for rational functions, I go to the numerator, degree of the numerator, and compare it with the degree of the denominator. Since the degree of the denominator is lower, I am top-heavy. And if you remember from Friday, if you're top-heavy, it means you have no ha. So my only suspect is 1, and that is the value of the whole. So I go to the function and I say, I replace g of x with 1, and I ask, excuse me function, will you ever equal 1? And I could plug in, whoops, my bad, I'm sorry, this is x plus 1, isn't it? So this is x plus 1, which means the y value is 3. So 3, excuse me. Excuse me function, will you ever equal 3? Now I could use the whole function, or I could just use the cleaned up, more simplified, get it, that's why you simplify, version, and I get x is equal to 2. But that is a bad x. So what does that say? That says conviction. So I know that this has no horizontal asymptote, this function, but it has a hole, and has a hole at 1, 3, and I know that 3 is not used for the hole, but it's not used anywhere else, so not a suspect anymore. I didn't have a horizontal asymptote to check, but I had a y coordinate of a hole to check, and it is indeed, I got a bad x when I did my algebra, which says you must kick 3 out of the range. No factoring to do here. I already identified my domain, so let's do the range. So the range is all real number, except for my suspects. Y coordinate of a hole, y coordinate of, or the y value of the horizontal asymptote. So I look back to my domain, my bad x was 5, from the factor x minus 5, which did not cancel, which means 5 is a va. So if I don't have any more bad x's, so I don't have any holes, no suspects there. To see if I have a vertical asymptote of a rational function, we look at the degree of the numerator and denominator. They are both 1. That's equal power. And if I have equal power, then I look to the ratio of the leading coefficients. Both of them had a leading coefficient of 1, and the ratio of 1 to 1 is 1. So my suspect is 1. So I need to go to h of x and replace it, because that's a y, with 1. And I ask, hello function, will you ever equal 1? And this is where I solve a rational, because unlike 0, when I was asking 0, I only cared about the numerator, but now I want to know if this rational function will ever equal 1 or 7, or if it was a different value, you just solve a rational equation. Here, since I'm equal to 1, I do know that x plus 3 must be equal to x minus 5 if your fraction is going to equal 1. My x's actually drop out, and this time I don't get a good x or a bad x, I get nonsense. 3 does not equal negative 5, that's just silly. So what was I asking? I was asking the function if there was an x that would generate 1. It's got nonsense. So that tells me that no, the function will never equal 1. Therefore, my suspect is convicted. My range is all real numbers, but y will never equal 1. So this function will not hit the horizontal asymptote at the ends, but it also won't hit it anywhere else. Remember, that's different from the first problem where the function will never hit the horizontal asymptote. Oh, this doesn't have a horizontal asymptote. Oh, yes, it does. It has a horizontal asymptote at 0. Right? So, and the function did hit 0. Bottom heavy, ha at y equals 0. Top heavy, no ha. Equal power, ha at y equals 1 over 1, which equals 1. Good? So again, remember homework here, 3 problems. This we're going to do at the end. Alright, ready? Let's move on. Sometimes I want to give you, you'll have to find the range not from an equation, but just from a graph, where you have to look. This is going to be really important. This is the twist that I was talking about. So I'm actually not going to do number 1 first. I'm going to do number 2. These red dots are supposed to be open holes. Right? This is an open hole at 0, 0, and a hole at 1, comma, I'm sorry, 1.5, because this is 1. So let's say 1.5. Comma 1. Okay? So when I look at this, also has a ha at y equals 2. This has a ha at y equals 0. So they didn't ask me about the domain, they just asked me about my range. So my range is all real numbers, but my suspects. I suspect y value of the whole. I suspect the y value of the ha. The y value of the whole is 0. And the y value of the ha was 2. If I had an equation, I would set it equal to 0 and to 2. I don't have an equation, so I just have to look. So, look at 2. Here's the ha. I know the function isn't going to touch it at the ends. You're going to slide here and slide here. Do you touch the horizontal asymptote in the middle? Anywhere. Right? Do you touch it? Does the function come up and touch it, cross it? No. So therefore, 2 is convicted. 2 is going to be kicked out of the range. What about 0? Here's the y value of 0. Do you use 0 anywhere else? Right? I don't use 2 anywhere. Do you use 0 anywhere else? No. Therefore, both of these suspects were convicted. And my range is all real numbers without, and you have to kick out 0 and 2. Because I use, now remember, what does this mean? This is going to be important for the next one. If you're saying the range is all real numbers except for these 2, that means that from negative, here I am on the y-axis, way down at negative infinity, there is a graph from negative infinity all the way to 0. Then there's a graph not at 0, but all the way from 0 to 2. And then there's not a graph at 2, but there is a graph from 2 all the way to positive infinity. That's what you're saying, that the only place the range is broken is at 0 and 2. So now let's go to the next one. I start off just as normal. I say my range is all real numbers, and I'm going to suspect any y value of a whole and any y value of a horizontal asymptote. So I suspect the 1 from the whole and 0 from the horizontal asymptote. 1 and 0. So now look at the whole. It is true that the whole is not used here, right? 1 is not used. That's an open circle. But look over here. This is a closed circle, and the height of 1 is used here. So, of my suspects, I have to write suspects. 1 not used over here, but is used on the left side, right? There's a point here that is maybe negative 1.5, comma 1, and it is a closed circle. So, suspect number 1 is clear. Leave 1 in the range. It's not used on the right side of the graph, but it is used on the left. Now look at the horizontal asymptote. Suspect. Is the horizontal asymptote ever hit? No, right? Because these arrows here, I know they're dramatic arrows, but they indicate that you slide. Slide. Don't touch. Slide. You don't touch horizontal asymptotes at the end. But what about the middle? Ever touched? No. So you do. Y equals 0 is convicted, not a suspect anymore. So you say the range is all real numbers, but y is not equal to 0. You feel very happy with yourself, and you should be, because you have followed all my directions. Then you get this quiz back, and this happens to you. -1. What happened? This range, you did everything I said. You followed the procedure, you did everything I said to do, and that range is wrong. That's because this is a tougher problem. And this is not one you would have to do algebraically. You would always have a graph, either on your calculator where you can graph it, or I will give you a picture like this. You're not ready yet to do this part without a calculator. I'm sorry, yeah, without a calculator or picture. There's no algebra that's going to give you this that I would expect you to do yet. This is the problem. You're saying that there is a graph everywhere except at 0. And that's not true. That's not true. Do you see it? You see why? Look here. There's no graph for any of these y values. Any of them. There's a break. There's a y break. How did I know that was going to happen? I have a local max. Where is that local max? When x is equal to 0 and y is equal to -1. So, look at your y-axis. Way down here at -infinity, there's a graph, because these arrows keep going down. -infinity, there's a graph to go all the way here, and there's a graph that even goes with -1. But then there is no graph. There's a gap. No graph. There's no graph at 0. You already know that. But after 0, there's a graph even at 1. Not over here, but over here. There's a graph everywhere else. So this description, all real numbers except for 0, does not take into account the gap. And I knew I had a gap. Oh, that's terrible looking. Gap. Because I had a turnaround spot here, a local max. And remember, I told you that you were responsible for finding any obvious turning point. Now there's lots of ways I can write this range. Here's how I choose to do it. I don't even write that. I use interval notation. And I say I'm using y's from -infinity all the way down here, all the way up to -1, and I use -1, hard bracket, because it's used for the local max. Then I don't use anything until 0, and I don't use 0. Remember, 0 was a suspect that was convicted. 0 is not used, soft bracket, but then I have a graph everywhere else, even at the value of the whole, because the value of the whole is not used on the right side, but is on the left. Okay, that's tricky. Now, what if this had also been a whole here, so that the y value of 1 did need to be kicked out? You know what you would do then? Well, you'd have to stop the range. You'd have to say, I use -1, but then I don't use anything to 0, I use everything from 0 until 1, and I don't use the y value of 1. Then right after the value of 1, I go from 1 to infinity. That's if this was also a whole on the left side. Okay? Tricky. So some of your homework problems were like that. So we'll look at that when we go over the homework. Okay? Oh, and also in the characteristic handout. Alright, so here's steps to determine the range of rational functions. So remember, this is rational functions. This is what I do. You identify your suspects, the y value of the ha, right, or the y value of the whole. So you have to know how to find a ha, right? Looking at for the rational functions, you look at degrees of numerator and denominator.
Here's our suspect.
The y value of the whole, right? It's a bad x that canceled out. And you find the y value by plugging the bad x into the equivalent. Equivalent, however you spell that, equivalent form. You replace f of x, remember, which is just a y, with each suspect and solve the rational equation. If you get a good x, leave that y value in the range. If you get a bad x, or nonsense, right? This is not, if you get no x but you get like -3 is equal to 5, that's the nonsense. Then you kick the y value out of the range. And then you need to add number 5. Look for any other gaps. You will have your calculator or a picture I'll give you for the gaps, right? Your clue that you're going to have a gap. Do you have any local max or min? That's your clue. Okay? So, I have the 3 warm-up problems again, and notice we're going to start talking about characteristics. So we already did domain and range. And with the domain and range, we also found wholes and asymptotes, right? The only thing we didn't do was find the intercepts. So we found the domain and range of the first warm-up problem, the vertical asymptotes, and the horizontal asymptote. How did I find the x-intercepts and y-intercept? Y-intercept, you plug in 0 for x. And you get your -3/8. X-intercept, you plug in 0 for y, and since it's 0, I don't care about the denominator. And remember, we got x is equal to -3, which is also, by the way, if you remember, how I figured out if the function hit the hit the horizontal asymptote. So -3, 0. How about the second one? The second one, how do you find a y-intercept? Plug in 0 for x, and you get -2 over -2, which is 1. To find the x-intercept, you plug in 0 for y. And remember, this canceled out, right? The factor of x minus 2 canceled out, and you were left with x plus 1. Right, so you can plug into the simplified version and you get x is equal to -1. So this was the domain that we'd already found, the range. We had no vertical asymptote or horizontal asymptote. We had found the whole at 2, 3, and now I just found the x and y-intercept. For the last one, y-intercept, plug in 0 and get -3/5. For the x-intercept, plug in 0 for y. Really, who cares? This is a good x. Remember, this was a good x. And there's my x and y intercepts. So we're on our way to our characteristic list. Now let's do some more. So this is a different function. It is not one of the warm-up ones. This is a picture I showed you before once when we were looking, but I do want to make it clear that this is a closed hole at 0, -1. And I hope you can see that that is a local max. What else do I have? I have a vertical asymptote at x equals -4, a vertical asymptote at x equals +3, I'm sorry, -3. I have a hole at -4, let's say that's -1, and this is at 4, I'm sorry, +1. This is a hole at -2, -2, and +2, -2. And I have a ha at y equals 0. So, look at all the characteristics that I'm going to ask you to fill out. Okay. So, let's go ahead and fill out what we can. Right? I see my vertical asymptote is x is equal to ± 3. I have holes at ±4, 1, and ±2, -2. I have a horizontal asymptote at y equals 0. Yes, rational functions are functions. No, this rational function isn't continuous. No, this rational function isn't one-to-one. I'm not continuous because of my domain. Right? I purposely didn't fill that out at first. Notice, my domain is all real numbers except x cannot equal ±4, ±3, ±2. I'm going to skip the range for a minute, and I'm going to go down here to max and min. You are at the point now where when I say max and min, you need to think local and absolute. I don't have to say it. You have to say it. So, these arrows here should talk to you about absolutes. Is there any absolute max or absolute min given those arrows? No. But what about local? You have a local max. You have to tell that to me. I have a local max at -1. Do you have any local mins? No. So I have a local max. That talk to me. Remember, maxes are range values, y values. You need to consider this up at the range, and I purposely left that blank as well. Look at your what else is a range value? Your ha. Is your horizontal asymptote touched or crossed? Slide here, slide here. Not touched. But you have a local max. What does that tell you about in between here? You've got a gap. So how are you freaking going to write this range? From -infinity all the way to the y value of the max, which is used. Then you don't use anything until the horizontal asymptote, which you don't use. And then what about the holes? You also have to worry about the y value of the holes, which, whoops, I didn't consider here. Notice that y value of -2, y value of -2. Two holes here, and -2 is not used anywhere else. So the range is -infinity to the y coordinate of the hole, not used. From the y coordinate of the hole to the horizontal asymptote, not used. From the horizontal asymptote to the y coordinate of the next holes, and since 1 is the value of the hole and it is not used in either branch or anywhere else, that's kicked out as well. Then from the y value of the hole, forever is the rest of your range. OMG. Take some thought. Now hopefully you can see here that you don't have any x-intercepts because you don't touch the horizontal asymptote, and that your y-intercept is that local max, which is -1. So you thought range was bad? What about increasing, decreasing? Remember, those are domain values. Remember this from Unit 2, first characteristic list? Increasing and decreasing are domain values. Look at your domain. You've got 1, 2, 3, 4, 5, 6 bad x's. So when you're increasing and decreasing, I can see what's going on. I'm increasing from the left side of the domain to the hole. Nothing happens. Swoosh. Increasing, swoosh up to the hole. Nothing happens at the hole. Increase to the max. How do you write that? From the left side of the domain to the x-coordinate of the hole, don't use it. From the x-coordinate of the hole to the x-coordinate of the vertical asymptote, don't use it. From the x-coordinate of the vertical asymptote, don't use it, to the x-coordinate of the hole, don't use it. From the x-coordinate of the hole to the x-coordinate of the local max, used. This, unlike the range, if you put a parentheses on 0, no one's going to care. How about decreasing? After the max, you're decreasing to the hole. Nothing happens at the hole, swoosh. Nothing happens at the vertical asymptote, across the vertical asymptote, swoosh down, swoosh. To the hole, nothing happens at the hole, slide. How do you write that? From the x-coordinate of the local max to the x-coordinate of the hole where nothing happens, you're going down. From the x-coordinate of the hole where nothing happens to the x-coordinate of the vertical asymptote, swoosh. From the other side of the vertical asymptote, swoosh. Down to the x-coordinate of the hole where nothing happens. From the x-coordinate of the hole, slide. OMG. Now I left these two boxes blank over here because you will not be tested on these. But concavity. Can you see concave up and concave down? Soup and no soup. Can you? The left branch here is all concave up, right? Soup.
Oh, yeah.
Except for the hole. The middle branch is all concave down, except for the holes. The right branch is all concave up, except for the hole. Right? Soup, no soup, soup. And you've got holes in your spoons. So how do you write that? Again, not tested. Concave up from -infinity to the x-coordinate of the hole, not used. from the x-coordinate of the hole to the swoosh. Then again, concave up over here from the x-coordinate of the vertical asymptote, swoosh, down to the x-coordinate of the hole. From the hole, slide. How about concave down? From the x-coordinate of the vertical asymptote to the x-coordinate of the hole. From the x-coordinate of the hole to the x-coordinate of the other hole. From the x-coordinate of the hole to the swoosh. There's no point of inflections on here because the places where you change from concave up to concave down is a vertical asymptote. Calculus is where you do all of this and you're able to find all of this without just looking. Okay, the whole gaps in the range, as well as the concave up, concave down, hold, all that kind of stuff, increasing, decreasing, that's one of the purposes of calculus. Alright, so this was a characteristic list from looking, which again you will have either a picture I give you or a picture on your calculator to do all of this for, and concave up and concave down not tested. Okay. So I'm going to make another video for going over the homework problems that you were supposed to do over this weekend, and tomorrow we'll be moving on. See ya!